controlling aspect. So by controlling means generating these signals, pulses, for synchronizing the data during transfer, stored in the memory during the process of data, plays the role and it manages the data flow. So managing of data flow happens through this control unit operation, execution of this control unit. It gives these high-low pulses, and the control unit follows the principle of the one at a time. Accordingly, it processes all the data. So it's all sequential here. So the input-output, like the electronic devices, the von Neumann architecture also has an input-output architecture. The basic function same is, nothing specially has been designed for this. So these are again very similar. Okay. So yeah, so von Neumann, any of the sort of addition, subtraction carried out by LU, so it does these things. So this is again an understanding of the So the accumulator block residing inside the ALU, it takes in data, processes it, and gives output, and then it interacts with the control unit based on these this high-low signals. This operates, and then it fetches. It may store in the memory, or it may take from the memory. Okay, so this is what is. Yeah, so this is again very generic, and then comes architecture with physically separate storage. So that is the difference here. The storage, both of them have storage, but here there is some kind of let's say partition or separate dedicated storages. Okay, and separate pathways are also separate storages and separate signal pathways for program, data, and instruction, as for the operands and the opcodes, I mean, which in turn makes it possible to access each of the memories simultaneously. It's just a repetition which employs single bus to fetch both the instruction transfer. One part has separate memory space for data instruction. So as I said, both of them are similar, except that the pathways are different, and there are dedicated memories for this for this opcodes and operands. Is to split the memory to two parts, one for data, the other is this. So basically it's the same thing, actually based on modified architecture commonly used in microcontrollers and DSPs. So quite highly used in such cases. So here you have this separate instruction memory, separate data memory, right? And then this control unit coordinates between them. Okay, it goes through this. Okay, so more features. The same thing. The instruction CPU, it interacts with data memory separately, program memory separately. These it has dedicated data buses for the program memory and data buses for data memory. Similarly, data bus for data memory and data bus for program memory. Okay, and this is the instruction cache. So quickly fetches this instruction and starts executing that. Okay. So it's used for processors and other devices. Yeah, so we'll talk about, I think pipeline is explained in the book to some extent. It's like, so that effectively it will look like the instruction sets are executed very fast, and because of pipelining, because of while one is being fetched, the other is being executed on this during the same time. And similarly, this also helps us to execute the fact that simultaneously we can access this data memory as well as program memory. So that also makes it faster. It can complete an instruction one cycle. The appropriate pipelining strategies are in place. So development of control unit in hardware architecture is more expensive because of the complex architecture that employs two buses for instruction. You have extra buses here, so that is why you have extra. It's costly. Architecture is able to read an instruction. It can also perform data access simultaneously at faster speed. So these are, so again, so that brings up some kind of comparison between this Harvard architecture and von Neumann. So in the case of conventional processors, like so this is mostly used in our laptops and PCs, and this is mostly used in for mostly embedded systems like DSPs, other processors for healthcare, automotive, mobile communication, audio, speech, and all. Both data are ignored in the same memory, or rather they are clubbed in the same memory. A separate memory is used. As you serially, it takes more clock cycles. Yes, it takes more clock cycles. Follows parallel level of coding because it can do parallel level. Right? You can do parallel executing. You can access these things parallelly. Okay, we'll find a large number of the multipliers. So more processing good will not find excess number of multipliers. So these multipliers are very much useful for mostly for DSPs, because the DSPs you have to do a lot of mathematical operations. So that's what it does. Uses same physical memory address for instructions and data. This we have talked about. Needs 2 clock cycles to execute. Needs at least 2 clock cycles to execute an instruction, or more. A processor needs 1 cycle to complete, or 1 or sometimes 2, but it can go up from 2 clock cycles to much more. Right? Simpler control unit design and development is cheaper because you have less buses to take care of. But here you have 2 buses to take care of. So control unit operation is complicated. Data transfer and instructions fetches cannot be performed simultaneously because you don't have supporting hardware. Data transfer and instruction fetches can be performed at the same time because you have, as I mentioned again, the same, you can separate simultaneously access them. Okay, used in microcontrollers and signal processing used in computers. So this is mentioned. So again, this is a quick understanding of the hardware architecture between the Harvard architecture and von Neumann architecture. Okay. So it's quite, hardware is simple here. The hardware is a little bit complex. You have separate dedicated memories. You don't have separate dedicated memories, single memory space, and then you have one set of data address bus, one data bus through which all this memory and output come here. Okay. So this is about one part of, this is the end of this thing. So now I'll ask you to ask you some questions, which we can go through. Okay. So can anybody ask doubts?
Sir, in the last slide where you showed the comparison between both, it was
Yeah.
written that von Neumann is used in laptops, but
Yeah.
if it is like if Harvard architecture is faster and also space
Hmm.
efficient, then why not use that in laptop?
Yeah, faster means, see, in laptops you don't need to be in real time. Okay, you must have seen, right, where people used to joke that Windows 2000 means it hangs 2000 times. So it's okay. I mean, if our laptops are slow, even if they are not real time, it's fine. It's a bit slower, right? We may manage with these laptops, right? So that is a thing. So but it can do a lot of because we use high level languages a lot. They are not dedicated things. So since we do these high level languages, that's why you have this CISC processor, because the CISC processor is good for these complex instructions. Okay, they are good. They can be mapped to these high level languages. That whatever we are doing, they are mapped to high level languages. Okay, and that's why this CISC architecture is better in these complex instructions. Okay, but for very dedicated simple tasks and all, those are good in this RISC architecture. That's why they are used in more embedded systems for small applications, but which are very fast to operate. Okay, so that is the thing. So we don't need, as I said, so we don't need this laptop or desktop to be in real time. It's fine. If it gets delayed. And I mentioned
Sir,
also that
apart from
part.
real time,
One minute.
it
About I
has
mentioned
like
another thing. Oh, no, I mentioned another thing. I mentioned another thing, that things are not so for CISC processor. Things are not so because it can, the instruction cycle, the execution time can be maybe for each instruction can be from 2 to 15, but not in case of this. Okay, so that's why this is again because of the complex nature of the program and all, but not for RISC architecture, in which things are more focused. See, in this case, this laptop that we have, it has to service thousands of variants of tasks, which we cannot even talk about. I mean, our sense. But RISC architecture, we know that this is how the architecture will, this is how the task will be for that. So we can optimize it in a better way. Things are much more predictable in the RISC architecture. That's why they're used for these dedicated processes, but not for this kind of this architecture. Not the RISC is not used for this because we don't have much control over that. Okay, yeah, you were saying something.
sir, I was asking more in the hardware part. Like it says that von Neumann is sorry, Harvard architecture is more hardware efficient. I mean space efficient. Von Neumann uses more space.
Mm,
So,
no, 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 no. Wait. I think it's the other way around. So
yes, sir.
space in what respect? See, we saw it here, right? If you see, just look at these two things. Okay, So here you have more address buses, okay,
Oh,
more
sorry, it's the
data
other way
buses.
around. Okay, okay.
Yes, the other way around. And this is more compact. So again, so there are multiple reasons. One is the legacy. So this CISC architecture was there earlier than this Harvard architecture, and then things have remained, and the softwares have been built to take care of that. And there are a lot of things, and then the hardware amount of hardware required is less also. Okay, so that is one thing. So but then yes, even if these embedded systems, they also they don't directly use, because if you use too many of these address buses, that also will increase the cost and complexity. And also sometimes in some places they'll still merge the address buses for both the program and this. In some cases it's between, let's say, between the CPU and the program memory, let's say, okay, or else it will be quite complex. Okay, so that is the reason. So as I said, one thing, so this hardware and software are highly integrated, right? So this and for our laptop or this thing, it uses it starts from the high level languages. A lot of applications are there, like your Word, like your Word or MATLAB. There are plenty of high level languages which have to be deciphered and converted to low level languages and then executed. So for that, that architecture is suitable. The CISC architecture is suitable for these things, and we know that we don't need to be very fast for that. Right? I mean, it can, and quite things can be a little bit unpredictable. So that's why things are being managed using CISC. So any other question?
So at the end, in whichever language we write the code, the processor actually executes the assembly language code. So, sir, I
Executes the binary codes of
uh,
the processor. Yes, binary, or let's say they can be represented in hexadecimal. Yes.
so sir, uh, so the binary code, actually executes the instruction sets which are already defined by the processor. For example, in the architecture itself. Like, am I right or am I wrong?
No, yeah. So for let's say that here in this case, so let us see from the example. Okay, here in this case, right? So these are the machine instructions. Okay, so they're like heavy instructions, so they have to be converted in the CISC architecture. So they have to be. You're talking from this perspective, right? So they have
Uh,
to be broken down. They have to be broken down, and then even if they have to be broken down, and they have to be, a lot of fetches and lot of processing have to be there. So that is why this will take more time. But in this case, the packets, the chunks of these instructions in themselves are small.
yes, sir.
Okay.
Yes,
They're
sir.
more optimized. But in this case itself, it is, these are like more complicated chunks of instructions. So they have to be further broken down, and then obviously everything will now execute in binaries, or before that, or hexadecimal. But for breaking them down, and so it's like, let's say that you have some complex instruction. Let's say that instruction A and this instruction B. We know that this instruction is, even though it is a big instruction, the entire thing has to be executed. Okay,
Yes, sir.
but here, this entire big instruction has to be executed. Similarly, this, even though it is small, this entire execution has to be executed. So this is faster. Okay. And this itself, I mean, this also has to be executed. So a lot of more number of instructions or sub instructions. You'll have more sub instructions. They have to be executed. So in this case, that's why yeah, that is why you'll have more time consumption here.
So,
But
sir,
but thing is
we,
that it can take care of more complex things. So here
so,
you might have to have more code memory here. Okay.
sir, can we say also, sir, it is something related. So, I wanted to ask if we can say that the time for fetching the instruction, the time required to fetch the instruction uses the data bus. So, so can we say that it is actually the limiting factor for performance of a CPU? Sir, because
That is one of the limiting factors. See, one is the structure of this sys, because the sys from the beginning the opcodes or the instruction there itself in a complex manner. They're mostly for complex things. Even if you're trying to do something simple, so it will be you have to use these complex instructions. Okay, most of them, but not in case of risk. So that is why the flexibility is more. Okay.
Yes.
Second is the limitation is also due to this factor, this factor, because here we look at this in the Harvard architecture. Quickly, I'm accessing. So it's not like in the CISC I have to wait. First, I have to wait to fetch the fetch the opcode, then the operand. No, here it's simultaneously I can fetch these opcodes and operands
Yes,
from
sir.
separate databases. So that's why it's faster, even though there are more obviously more hardware required. Hardware means more channels and all.
Yes, sir.
But in that case, that is another reason why. Yeah, so that is another reason you have to split it. You have to say, okay, you have to schedule it. Now I'm fetching now I'm fetching opcode. Now I'm fetching operand. Well, it's not like this. I can fetch these separate things. I don't have to wait for the address bus. I don't have to say that, okay, this address bus is now to access only operand. This address bus is there to only access the opcode. No, they are separate dedicated buses. So quickly you can do these things for Harvard architecture. So that's what makes it faster.
Yes, sir.
Yeah. Any other questions? Okay. Any questions from from the book? Any questions from the book?
Yes, sir. I had a question from the book.
Okay.
In sir, there was in DRAM there was given packaging. There was a topic packaging issue of DRAM.
Hmm.
It said that see, DRAM uses capacitor instead of transistor.
Yeah.
So because of uh, a large number of cells in the RAM, it splits the address in half and sends all the addresses through the same pins. Like, I don't understand how that would happen if it splits all the addresses into half and sends them together.
No. One minute. Can you just let's
So
see
should I
that
read the exact line?
No, no, no. Please show me the
Okay.
thing. Whether their interpretation is correct or not, I just want to see that. Okay. So which page number?
Sir, it's page number 40 of the PDF.
Okay. 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 So this is what you're talking about.
Sir, 4040, packaging issue of DRAM.
Packaging issue of DRAM. No, you're talking
Sir,
about
no, not
ZL.
of the book.
So
Uh,
page 24.
Sir, page 24 of the book, but 40 in the PDF.
Okay. Okay. Yeah. See, there is a problem packaging a large number of cells into a single chip with the normal number of pins assigned to address. A 64-bit must have 16 address lines and one data line. Okay. Requiring 16 pins to set the address if the convention is used. This is in addition to VCC power. And so can you tell me which line you have interpretation? What is that
Yes,
thing?
sir. Just it's written multiplexing, demultiplexing. The next line of that.
To reduce the number of pins needed for addressing. Yeah. So do you understand this multiplexing and deep learn multiplexing?
பைத்தியக்காரனா இருக்கேன். ஒரு இதுல மல்டிபிளெக்சிங் டீமல்டிபிளெக்சிங் நமக்கு என்னன்னு புரியலன்னு கேக்குறான். 4 லைன் கீழ அவங்களே எக்ஸ்பிளனேஷன் கொடுத்திருக்காங்க அந்த புக்ல.
It's something about overlapping the
படிக்கிறது அந்த சாப்டர். அவன் 5 படிச்சிருந்தான். அட்லீஸ்ட் ஒரு சாப்டர் முழுசா படிச்சனாலே அத பாத்துருப்பான்.
Hello.
Yes, sir.
Yeah. So first of all, do you understand this multiplexing and deep multiplexing?
Yeah, sir. When I googled it, I understood that it is combining the signal and sending it as one signal.
Not like that. So multiplexing means the same pin will behave as having two functionalities. Okay. So in this case, I think some other people also asked this question in the previous class. Not for this, so some other ECS class. So I'll just mention that. So if you're talking about this, to reduce number of pins needed, so same. Let's say that 16-bit is there, right? So you have this. So you have this higher address bus and lower address bus. So the same 8 bits of the pins are used. Once it is used as higher bus, and then in the next slot, the same pins are used in the lower address bus. Okay. So in this way, you're like overusing that. Okay, overusing these pins. So that's why so that's why the number of address the address pins required are less. Okay. Should I talk in more details?
Oh, no, sir, I understood. I mean, because there are 16 address lines, so that is why
Yes.
we put it in half and half, because 8 once and 8 the next time.
Yeah, 8 the next time for the same. They're overusing. They're using the same pins over and over again. So once this first set of pins will be used for the, let's say, higher address bus, so they'll locate the group of memory cells that are required, and then in the next, and they know that this is for this memory locations, and then it'll in the next iteration, next step, what will happen is then the same, let's say that you have these address pins. Because of these address pins, this will get so the lower address pins, they'll pinpoint exactly which memory location that will be used. Okay, it's clearly mentioned that the method used to split the address in half and send each half of the address to the same pins. Okay, each half, the same pins will be using the same thing. Okay, there are going fewer address pins. So the square and row will tell me the exact pinpoint. Okay, after the end of this address, lower address, you'll pinpoint the actual memory location. Okay, yeah. Next.
Sir,
Yeah.
sir, how is the product of the address pin and the data pin gives the total number memory? Means
What is it?
how the product of the address pin and the product of the data pin, it gives the total number of memory. How that is happening?
1 minute. So yeah, this one. This is what you mean, right? This is what you mean. Using addresses, how you are using
Yes, yes.
addresses, how you're trying to access this, right? So this uses a decoder logic actually. Okay, so this decoder logic, let's say that these are the higher address pins, bits. So this will tell you that, let's say this is here in this case 0011, okay, or 1100. So whatever, based on how you look at it, let's say that A15 is the higher one and A12 is the lower one. And so if this is 11 and this is 00, then only this will become what, 1, and then only this will become 0. So this memory chip will get what, this will get selected. Similarly, the moment this is done, then you use this set of addresses. Okay, this is the next set. The next set will be what they will do is they will use this because it is already selected. So whatever these bits are there, it knows that it is meant for this chip only, because this chip has got selected. Okay, and then then this is already selected. It means that this is the intended chip, and then all you need to do is give the values of this A0 to A11, and then the particular memory location will be selected. Okay, so that's why it's a combination of both the things. Okay, and besides, they'll be again coming the CPU. From the CPU will also come to know whether this address will be accessed in the read mode or the write mode. That depends on whether this is active low or whether this is active low. Okay, that means if this is 0, then the purpose for which to access this memory chip will be in read mode, or else if this is in the write mode, that is if this is low, then the purpose will be to write into that. Okay, so you can access the memory, right? You can access the address pins for two purposes. One is for read purpose, the other is for write purpose. Okay, does that answer your question?
Yes, sir. So the
Okay.
data is coming through the D0 to
Yeah,
D7.
they are separate. Yes, they'll come from a separate thing. Data is separate, address is separate. Okay.
Thank you.
So to put it in write mode, we need one active low and one high, or like there are
Which
4
one?
combinations now. So both active low is read. So what is the other one?
No. Both active low is read. That time this will be high. So suppose you're in reading mode, then this will be high. When this is so it's so whatever function you want to do, you have to make it low here. So that's why it's called active low. Suppose I want to access it in the form of reading mode, I'll make this as low, that is 0, and this, and maybe this as high. Okay. I'll just check. Selection 539. So these are old things. Need to latch some set using some latching. The deployment of high number of addresses counted using multiples. Alright, yes. Okay, so what are more data lines are required in Harvard for them? Okay, any other questions?
Sir, why does DRAM store 1 bit in every address location, whereas SRAM stores 8 bits in every address location?
Where is it written? Let's just trying to understand where you have read that. I just wanted to understand the context. Okay, so that's why I'm asking these things.
Sir, I think this is on the same page 40.
Yes.
24. Okay.
Yes, sir.
Okay. Yeah. See, by the way, it is, you know what DRAMs are, right? So they are like set of capacitors. Okay, small capacitors which get discharged very fast. But SRAMs are through this transistors. Okay. But why are you saying that they store 8 bits? Where have you written, where have you seen that? Can you just show me the
Sir, it's
sentence?
in the previous page.
Okay. Okay, in this, Intel going to introduce first dynamic RAM, random access, and its density was bits, and it is used as a capacitor to store each bit. Using a capacitor to store the number needed to build the cell. However, it requires constant refreshing. This is in contrast to SRAM, whose individual cells are made up of flip-flops. That's fine. Since each bit in each bit itself uses a single flip-flop, okay, it uses a single flip-flop, and each flip-flop requires 6 transistors. Okay, that doesn't mean that it stores 6 bits. Okay, so each flip-flop requires 6 transistors to generate this flip-flop. Okay, which will just give 1 bit. Okay, it's not 6 bits, it's 6 transistors to generate this. Okay, so you see that you get that.
Sir, in the organization of SRAM, it was 64K into 8. Like
No,
in
okay.
all the SRAM organizations, it was into 8. But whereas in case
No.
of DRAM,
One minute. So no. This are you clear about this thing?
Yes, sir. This one is
For the
clear.
single bit, for getting the single Q output, you'll be using these 6 transistors. Okay, Q or Q bar. Okay. Now coming back, what is your where do you have the doubt? Can you just tell me where?
Sir, in DRAM organization, everywhere we have into 1, whereas in SRAM organization, we have into 8.
No, into 8 is what? I don't get,
Like
get
2K
it.
into 8.
No. Where have you shown?
They have in several tables, they have mentioned the organization of.
Okay, why don't you show me? Why don't you tell me?
Let me open the PDF once.
Yeah. So again, this is to ensure, there is no
page
confusion.
23.
23, sir.
Okay. Page 23. Okay. This is the organization SRAM. This is the NVRAM. This is again 8. I don't see any 1 there.
No, in SRAM it is 8, but in case of DRAM, page 25, it's all 1. Mostly 1.
Where?
Page 25.
Okay. So in this discussion, we noted that all these chips have 8 pins for data.
In a table, sir. In a table. You can scroll more. 25.
Okay. So this is in the organization for this. So this
Even
is
here we have only one D in and D out, whereas.
Okay. Note that all these chips have 8 pins of data. This is not the case for DRAM memory, which can have. Okay, it can have. It's not like this. It can have 1 cross 4, cross 8, or 16 organizations. Okay, it can have. So in memory chips, the data pins are also called input output. In some DRAMs, there are separate D in D out pins. So yeah, shows this DRAM with pins this to this. Okay, so this can have means for more simple applications. Okay, so you can do that. That's why it is showing this. It is for more simplified applications. So it's not like cross one. It can be 4, like it mentioned. It can be 16 also. It can be 8 also. Okay, so that is the flexibility it has given.
Okay, sir.
So that is the flexibility. But as I said, these are for maybe, let's say, for simple applications. So that's why maybe in those cases you don't need all 8 bits. Okay, so then there are 8 bits, just one pin signals. Yeah, so it can be 4 pins also. Yeah.
How to find the size of an instruction, sir? 2-byte instruction, 4-byte instruction.
Oh, that is architecture actually. So that is given. I think that is given in, first of all, a lot of things are given here in instructions. You'll see in the succeeding chapters. Right? You'll see in chapter 2. Chapter 2 you'll get chapter
In
2 and
chapter
then
2, they
appendix.
have mentioned a few instructions as 2-byte
Yeah.
instructions and a few
Yeah,
as
yeah.
4-byte instruction. But
Yeah,
how do they decide?
yeah, and then there's something called the appendix. In the appendix also, it's hanging. Where is it? Where is it? Yeah, so that is not something which you can, yeah. So these are, yeah. So that is not something which you can fire. Yeah. So those can be in the data sheets also. Okay. So that is not what you can control. Okay. These are all hard coded in the. These are all hard coded in the architecture of that. So you cannot do anything on that. Okay. Like these branch instructions and all. So these are part of the architecture. Okay.
Okay, sir.
Yeah. Next. Okay, so here it is written, right? See, add instructions format. So here it is written in cycles 1, 2 cycles it takes. Then AND operation, it takes 1 cycle to this branch. The break cycles 1 or 2. Okay, PRLO. Okay, yeah. Next. So you can go through this appendix. Yeah. Next.
Okay, sir.
Hmm.
Can you explain little Indian and big Indian?
Okay, it is the way, the order in which the see, memory, you know, that this, that's a memory, this high byte and low byte will be there, right? So the high byte will have higher weightage and low byte has lower weightage, right? So this is the way they are kept in the memory, little endian and big endian.
Sir, high byte and low byte means first nibble and the last nibble. What
Yeah,
is high
that way.
byte?
Yeah, high byte and high byte, not byte, the high nibble and low nibble. Okay, high byte means the high portions of the memory. Okay, as I mentioned that, let's say that you have some number called 10101100 or some 8-bit number. Okay,
Okay.
so which has higher weightage, the first one,
101,
right?
first floor.
Yeah, and the lower ones have lower weightage, right? It is 2 to the power 7, to the power 6, to the power 7. So what happens is different processors, they have different ways of storing these numbers. Okay, some of them
Okay.
will keep the the higher values in the lower memory, and lower bytes in the lower nibbles in the higher memory, and
So
similarly it's like,
lower memory and higher memory means the number denoting the address.
yes, the address, yes, the
Okay.
addresses. So
Okay.
they'll be kept in that. So different processors have different things. So we actually, I'll tell you, when actually I was working in Sweden, that was in the year 2006, and then we were communicating with 2 processors. Okay, so we were making the processor for the central. There was something called the central processor unit board, and it was used for this telecom exchange board for Ericsson. Okay, and then what was happening is we are getting a lot of garbage values and all, a lot of high values and all. We could not understand why. What was happening was there were two processor boards. They were communicating with each other, and the way they have stored their memory. So some of them, the high values they store in the address places, and the other processor was using, so one processor was using little endian, the other processor was using big endian. So the interpretation was wrong. Okay, so because of which it created some confusion, and then we were interpreting some high values, because we have to convert, right? Basically we have to convert them into into decimal and all. So while doing that, we have to multiply, let's say we have to convert from binary to decimal, right? So what do? We have to multiply with the weightage factors, right? So if we interpret it as wrong, right? If we interpret it as wrong, then we'll use the wrong weightage factors to recreate the values of the binary values. Okay. So that is what is creating the problem. So that is the thing. It is the way they are kept in the memory. Okay. So, but you have to be very careful. Okay, which processor has which thing? Intel will have something. Some other processor will have something. Okay. So it's just about the placement of the bits in what order while it is residing in the memory.
Okay, sir.
Yeah. Next.
Sir, in page 78 of the book and in several other places, LOC is mentioned. What is LOC?
Where?
Page 78, I think it's the first occurrence. 93 of PDF, 78 of book.
93
of the PDF. 78.
Okay, 93 of, okay, I think I'm coming close to this thing. Yeah, 78, right? Now tell me.
Somewhere in the
they?
comments it was written LOC.
LOC.
Assign RAM LOC to some. In the comments of the
Okay,
before
okay.
dot
Store the
org.
result in LOC.
RAM,
I
like in
forgot.
several places in the comments they have mentioned LOC. What is it?
Assign location, I think.
Okay.
This is the location, yeah, in short form. RAM location to some. So this is the location of the RAM through to which you are trying to access. Okay, whose content you're trying to access. So that's why you're using this, is because this is a location. That's why you're using this STS, because it will access through the location. Okay.
Yes, sir.
Next, but you're going through these. These are very important. You know, these programs and examples are very good actually here in this book. So are you going through them? Are you understanding these examples?
Yes, sir.
Okay. Okay. Next, any other question?
Sir, page 114.
Which
Book of
book
the book.
name of the book? This one? Or 114 of the book? Okay. So something into chapter 3. Okay. 114. Yeah. Tell me.
There was that in this there is a column called machine that there.
The column called, oh, this is, yeah, this is machine. These are in hex actually. Just convert that to machine
Means
code.
that this code that LDI
Yeah, yes,
R210,
yes.
it is always E050 always.
Yes, 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 yes. For this is the equivalent code actually. Okay.
So, but there you see that where was INC R21. Here is 9543 and here is 9553. Why that is different?
No, but here you have this increment now. So, but 9353. So this is the 9543. Okay. So one is carry increment now high byte. Okay. Branch 9553 and this is 9543. Okay, I think there is something to do with, I forgot about this.
And so I am asking the question that
What are they
all the
saying?
instructions are stored like this. LDI register this to this or that to that. Means
Yeah.
all the instructions are stored.
Yeah, stored where actually? So these are low level. Actually, they are converted to. So it will not be like LDI. This they will be converted to these hexadecimal numbers. Okay, these are hexadecimal numbers. Okay, they are converted to equivalently hex file. So this is equivalent hex file. But I think there has to do with something um, with the branch or something. Some this 10, this extra 10. I think it has to do with something with the location in which it is trying to access. Because of that, some location problem is there. That's why I think there is some location thing. That's why I think it is using this. Okay, so or else if you see add R20 this, and you have another add R20 this. Okay, look at this, add R20 R16. Here also you have add R20 R16. So here in this case you have both the same code, right? 0F40, here also 0F40. Okay, but here I think it has to do something with the
Sir, actually, this
location.
one is explained in page number 102 of PDF.
102 of PDF. Yeah,
PDF.
yeah. 102 of PDF before that.
Yes, sir. Before.
Oh, here, you mean here? Okay. Yeah. So machine code is, let's say E205, where E is the opcode, and 205 is the operand. Okay.
Sir,
So
in this manner, actually, it is stored E205. One is opcode, and those two are for the
yeah,
operands.
yeah. But the question is, if the instruction or operand are the same, why different? Why they are different values? Okay. Why the machine code is different for this?
No, sir. 110, sir. That one is the part of opcode, and other KKDD are for the operands. So when operands will be different,
No, but
the
operand is same. Operand is same for both the cases. Operand, yeah. So operand, okay. So you're saying the value of the operand, right? Yes. So this will be packed to the value of the operand. Okay. Yes. In that case, so these are the, yes. So this is the, one is the value of the operand and the other is the opcode here. So what was it using in that way? Let's say in that case, was the value different or same? So that we can find out. What was that?
Page 114.
Yeah. So in this case, you have, this is R21. So R2, so here in this case, see this and this are same because, so 0F40 and then, okay, 9543 increment, now high byte is equal to 0. Okay, then you have 9553, now high byte is equal to 1. Okay, so yeah, so big, because maybe the value of this is now different, so that can be another possibility. Okay. But I don't know what the value is. So I thought I was using that value as same, but maybe the value is different. But in this case, it is, but in this case, let's say here, right, branch N1 and branch F2. So look at this thing, F408 and F408 both are same. Okay, branch 2, but here it is N1, this is N2. Okay. So this again, BRSH, I think some of them have to do with the address also, but I wonder why the addresses are different, because BRSH and this, they also depend on the address. Okay, so the address or the location. So where is your N2 and N1? So this is your N2 and this is, where is your N1? This is your N1. Okay, so this is your branch to this, but both of them have their own, but yeah, both of them have, this is N1 and this is N2. Yeah, this is N1 to N2. So here you have different memory locations. Okay, but still, in spite of that, this is there. So yeah, so those are given actually. So those are just standard conversion to machine codes. So yeah, this is also mentioned actually here. The BRSH, notice that the jumps forward, the target address for a forward jump is calculated by adding the program counter of the following instruction to the second byte of this. Okay, so in line 7, the instruction has the machine code F408. This is what I was trying to say. to distinguish the operand and the opcode parts, we should compare the machine code with the instruction format. In the following, you can see the format for the instruction. The bits marked K are the operand bits, while the remainder are the opcode bits. The machine code equivalent is, if we compare it with the BRSH form, you see the operand is and the opcode is this. The 01 is the relative address. Oh, so yeah, so the relative address may be the same here. So I think that is the reason. Okay, so because this is BRSH, it deals with the relative address. So because the relative address here, look at this here, if you go here, NAN2, the relative address is what? The relative address is around 1 or 2 here. And similarly, the here also, if you look at here, N1, the relative address is again, 2 places from here, 2 or whatever places from here. Okay, so that is the thing. So it is not, it doesn't use the absolute value of the address. So because the relative address is the same, so that's why you have the same, you have the same code. Okay. So yeah, so next. Next, any other question?
Sir.